integer multiplication and division. Now, what we have seen simple arithmetic instructions, addition, subtraction. I talked about logic operations like AND or XOR. We have seen the shift operation. We can use the shift actually for multiplication. If we shift to the left, we can also use it for division if you shift to the right. But let me talk about multiply and divide instructions, because these exist inside the MIPS architecture, and we need to understand these instructions. And they are also very useful in programming. So I'll talk first about integer multiplication. I'll show you how we can build a multiplier in the hardware, how we can design a circuit that does multiplication. I'll talk about division, and I will talk about the instructions that exist in the MIPS architecture for integer multiplication and division, and how we can use them in programming. Okay, so this is the topic of this presentation. Let me introduce first integer multiplication. Suppose I would like to multiply two numbers, okay, in binary. I'm going to assume that these two numbers are unsigned. So here I'm not dealing with negative numbers. I'm dealing only with unsigned integers. So the first number is called the multiplicand, and the second number is called the multiplier. So suppose I would like to multiply in binary, I would like to multiply 12 by 13. So I'm going to restrict it here to 4 bits, just to illustrate to you how you can multiply integers. So integer multiplication or binary multiplication is very simple, okay? So in the case of multiplying by 0, okay, so you take each bit here of the multiplier. Okay, let me use my, I need to use my highlighter here. Okay, so you take each bit here of the multiplier, for example, this one, and you would like to multiply it by 1100, so you get 1100. So if you take 1 and multiply it by the multiplicand, you get the multiplicand. And if you take 0 and you multiply it by the multiplicand, you get 0. Because 0 multiplied by anything is equal to 0. So you can see that binary multiplication is so easy because you only have 2 digits, 0 and 1, right? Now notice that here this bit is equal to 1, so you get the multiplicand again, 1100, and this bit is equal to 1, so you get 1100. But the most important thing is that you need to shift, okay, because each bit here has a different weight in the multiplier. So this is why we need to shift. By shifting, you are inserting zeros here to the right, but I'm not showing them. I'm just leaving it as a blank. But really, you are inserting zeros here from the right. Now, once you have done this, okay, these are the partial products. What you have to do is that you have to add them up to calculate the final product. So we add the bits vertically. And if you add the bits vertically, you get the final product. So here you drop the 0. This is 0 plus 0. Of course, you have zeros here below that, but I'm not showing them. So this will give you 0. Here, 1 plus 0, you get the 1. 1 plus 0, you get the 1. You get the 1. 1 plus 1, 0, and the carry. Okay, so maybe I need to write the carry here. Let me show you the carry, okay, with my pen tool. So this is here, 1 plus 1, 0, and the carry. There is a carry here. Okay, oh, sorry, my handwriting is terrible. Okay, so 1 plus 1, 0, and there is a final carry. And this final carry here, we just drop it. Okay, so that's here my final carry. So now this is my final answer here in binary. And if you look at this number here in binary, this is 156 in decimal. Okay, in fact, if you multiply 12 by 13, okay, in decimal or using your calculator, you should really get 100. So it should really give you the same result. But the way that the hardware does it does it in binary. Okay, so all the arithmetic which is done inside the CPU, it's done in binary. So the circuits are designed to operate on binary numbers. So we have a circuit that does this, okay, multiplication. Now, one thing about multiplication is that if you have an n-bit multiplicand multiplied by an n-bit multiplier, you get 2n, the number of bits in the product. So I'm multiplying 4 bits by 4 bits. The product will consist of 8 bits, double number of bits, okay? That will be the number of bits in the product. And this is accomplished using shifting and addition. Okay, so notice that I shift and then I add. Okay, that's basically how it's done. Of course, designing a circuit that does multiplication is going to occupy more area on the chip, and also it will consume more time because we have many partial products. For example, if you would like to multiply 32 bits by 32 bits, how many bits you will have in the product?
64.
Yes, 64 bits. Exactly, 64 bits in the product. So you will have 32 partial products. So you have to shift, 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 okay? You will have 32 of these, and then you have to add all of them to get the 64-bit product. So for this reason, you need more adders, okay? It takes more time. So really, the size of the multiplier becomes large, okay? In the CPU, it will occupy more area on the chip. This is the multiplier, okay? It's really simple. You can really understand that. You can do it by hand, binary multiplication using a paper and a pencil, but you can also design a circuit that does exactly this. Okay. Now, in the case of signed integer multiplication, if you are dealing with negative numbers, okay, one way to do it is that to convert the multiplier and multiplicand into positive numbers. Yani if you would like to multiply two negative numbers or one negative with one positive, if the number is negative, you can convert it to positive. Very simple. You can take the 2's complement. So the 2's complement of a negative number will be positive. And then you multiply the unsigned multiplication after converting all the numbers to positive, multiply the positive numbers. So this is like the unsigned multiplication. And then compute the sign of the product. And if you have, let us say, both of them are, let us say, positive, the result will be positive. If both of them are negative, the product will be positive. If one of them is negative and the other one is positive, then the product will be negative. Okay? Now, if the product is negative, if you have one of them is negative and the other one is positive, then you know that the product sign is negative. So after multiplying doing the unsigned multiplication, you have to take the 2's complement of the product to convert it to negative. Okay? The drawback is that you need additional steps. You need to take, you need to check the sign, you need to take the 2's complement, and then you have to take the 2's complement of the product at the end, and this will take more steps and more time. There is a better version, is that we use the same multiplication hardware that we use for unsigned multiplication, but we extend the sign of the multiplicand, and we check the multiplier. If it is negative in the last step, we convert it to subtraction rather than addition, because the weight of the most significant bit in the case of the multiplier, if the multiplier is negative, the weight of the most significant bit is negative. So when you multiply by a negative number, you have to, rather than adding, we subtract. It's a small trick that we can do, okay, in the hardware to simplify the hardware, and we can make it faster. I'm going to show you an example about this. This is signed multiplication done by paper and pencil. Now notice that I'm showing here two different examples. In the first case, the multiplicand is negative. Now this number here is signed. Okay, it's not 12, it's -4. Now notice that I'm just showing it for 4 bits. You can do it, of course, for whatever number of bits, but I'm showing it only for 4 bits. Notice that the sign bit here is 1, indicating that this number is negative. So this is -8 plus 4, it will give you -4, because the weight of the most significant bit will be negative. It will be -8. And this is 4, it will give you -4. Now this is positive. You can see it's 0 here, and this is +5. So when you multiply -4 by +5, you expect the product to be -20. So let us multiply. I'm going to multiply this one, okay, of the multiplier by 1100. This is 1100. But the idea is I have to do sign extension because the number is signed. You cannot assume that there are zeros here. No, you have to do sign extension. Okay. So this will be -4, which is sign extended. It will remain -4 after doing the sign extension. So whenever you are dealing with a signed integer, you have to, and you would like to extend it, you have to use sign extension. This is the rule, okay? Now, this 0 will multiply, it will give me zeros. I'm going to skip the zeros. And this one multiplied by 1100, this is 1100, which is shifted twice, okay, based on the position of this bit. And then it is also sign extended. Now, when you add the numbers here, you will get this one. Now, you will get the final carry, but this final carry is ignored. Okay, it is ignored, it's discarded. Okay, so if you look at the value of this number, this is this sign. Now, this is negative 128 plus 64 plus 32. This is plus 8 plus 4 will give you negative 20. You can just add the weights, and this will give you negative 20. So we get the correct product at the end. So, so you can see that we can use the same hardware that we use it to do unsigned multiplication to do signed multiplication. So you can actually have two types of multiply instructions that exist in the hardware, one that does unsigned multiplication and the other one that does signed multiplication. And the number of bits, remember that we are doubling the number of bits. So we have 4-bit multiplicand and 4-bit multiplier, so the product is 8 bits. Okay, it is 8 bits. Now let us take a look at the second case, which is negative multiplier. Now, if you look at the value of the multiplier here, it's negative 8 here. This is the sign, it's negative 8. And here plus 4 plus 1 plus 5. So minus 8 plus 5 will give me negative 3. So I'm multiplying negative 4 multiplied by negative 3. I expect the product to be positive because when you multiply negative by negative, you get a positive product. Now, I would like to multiply them, but without converting, without taking the 2's complement of the multiplicand and the multiplier. I mentioned that one way to do this is to look at the multiplicand and multiplier, and if they are negative, you can convert them to positive by taking the 2's complement. But we are not going to do this. We'll just keep them as they are. We'll just keep them negative, and we'll just multiply them directly. Now, the trick is that when you are multiplying by the most significant bit of the multiplier that has a negative weight. Okay, so as before, okay, we take each bit of the multiplier and we multiply it by the multiplicand and we do sign extension. So the least significant one multiplied by 1100 is 1100. This is just my multiplicand and it is sign extended. Then we take this one, okay, that has a weight of 4, and we multiply it by the multiplicand. We get the multiplicand, and then it is sign extended. Now notice that, again, I'm just leaving here spaces because I have to shift to the left because the weight of this bit is 4. Now, this is actually for all of these bits except for the most significant bit. Now, the weight of the most significant bit is negative. So I'm multiplying the multiplicand by a negative weight. So in order to do this, I have to take the 2's complement of the multiplicand. So only for the most significant bit, when you multiply by a negative weight, then therefore you have to shift. So basically you are multiplying the multiplicand here. This is my multiplicand. You are multiplying it by this bit, the most significant bit. And this most significant bit has a weight of negative 3. So we shift to the left by 3. We shift to the left by 3 bits. So these are just 3 zeros. And we write the multiplicand, but the multiplicand, we have to take the 2's complement of the multiplicand. So when we take the 2's complement, it's like subtraction, okay? So, so when we take the 2's complement of the multiplicand, so we leave the least significant 0 until we encounter the least significant 1. And we complement all the bits that appear to the left of this least significant one. So these ones become zeros. Now, by taking the 2's complement of the multiplicand, we are just doing a subtraction, okay, in the last step. Now, only what we have to do is that we just have to add to the 2's complement of the, we just have to add to the 2's complement of the multiplicand. So by adding zeros, you get 0 here, okay? Now, when you add 1 plus 1 plus 0, you get 0 and the carry. So let me just put a small carry on top of this one. I don't know how to fit it. Okay, I'm just going to draw it on top. Let me clean up here, just erase this arrow. Okay, and use my pen tool again. So 1 plus 1, 0, and the carry. So I'm going to put the small carry on top here. 1 plus 1 plus 1, we get 1 and the carry. 3 ones. Okay, so I'm sorry, we're adding 4 ones. We got 0. Okay, and then we got a 0 here, and then we have a carry. Okay, so let us take a look here. Okay, in this column here, I have 4 ones. So 4 in binary is 1, 0, 0. So the sum is 0, the first carry is 0, and the second carry is 1. This is important when you are adding, okay, many bits vertically. So we have here 3 ones plus a carry. So we have 4 in total. We are adding 4 ones. So 4, 1 will be 1, 0, 0 in carry. So we got a 0 here for the sum bit. Okay, the first carry will be 0, the second carry is equal to 1. So we have to be very careful about this. Now 0 plus 1 plus 1 plus 0, we get 2, right? So we put a 0 and there is a carry on top of that. So now we have another carry. And now we have 1 plus 1 plus 1 plus 1 plus 0. Okay, so we're adding all of these 2 carries plus these 2 ones plus this 0. We got 4. So now we got 0. Okay, and then we can ignore the rest. In fact, all what we care about are just these 8 bits. And if you look at the value of these 8 bits, it will be positive 12. Now, of course, we are going to get here 0 and a 1 as a carry. But as I said, okay, so we got 0 and a 1. Because the sum here is 4, because we're adding 4 ones. But we can simply ignore these. So these are ignored. Now, you may say that actually why you are ignoring them. All what you have to do is that imagine that you are extending these with ones. Okay, so here you can imagine that the first partial product, you are extending it with ones. You can extend it with ones to infinity. Here you can extend it to ones into infinity. And here you can extend it with zeros. Okay, after taking the 2's complement, you can extend it with zeros to infinity. So if you repeat this, you will get all zeros here in the product. But there is no need to do this. So basically, we got the correct product, which is plus 12. Okay, but because we are adding here 4 ones, so let me just erase. This is a 0, it's not a 1. Let me just rewrite it as a 0. Okay, it's clearer now. So because we are adding 4 ones vertically, this is the number 4. So the number 4 in binary, you get the least significant bit is a 0. Okay, the first carry is a 0 and the second carry is a 1. Now here we are adding 2 ones, you get 0 and another carry. So we have 2 carries on top of each other. 1 plus 1 plus 1 plus 1. So you get 4. So you get the sum equal to 0, the next carry is equal to 0, and the second next is equal to 1. So when you have like many partial products and you are adding bits vertically, okay, you might actually get, okay, it's not just the next carry, but you might actually get the second next carry and so on. So this example shows that if you multiply 2 negative numbers, the product will be positive. If we just do sign extension to the partial products, you will get the correct answer. But in the last step, when you are multiplying by the most significant bit of the multiplier, now if the multiplier is negative, okay, in the second case, what you have to do is that you have to take the 2's complement of the multiplicand. Okay, you have to take the 2's complement of the multiplicand. If the multiplicand is negative, you get it positive. So the 2's complement will be positive, and then when you extend with zeros. If the multiplicand was positive, you get a negative. So here you get actually a negative. The 2's complement will be negative, and once extended, it will be extended according to the sign bit. It means it will be extended with ones. Okay. Is this clear? So these were examples about how we can do signed multiplication by paper and pencil. طيب, let us continue. Okay, if you want to build a multiplier, you can do it in different ways in hardware. People have suggested different designs for a fast binary multiplier. I'm going to show you how we can multiply this, how we can design a circuit, okay, to do fast multiplication. So suppose I would like to multiply only 4-bit numbers. So in this example, my numbers are restricted to 4 bits. So this is A, it consists of 4 bits. And this is B, that also consists of 4 bits. Okay. Now, for simplicity here, I'm going to assume that my numbers are unsigned, because in the case of signed, what you have to do is sign extension. We will not really do this. Okay. So in the case of signed multiplication, the circuit will be slightly different. Okay. And people have shown how you can build really very efficient, very fast multipliers, even for signed integers. But for simplicity, I'm going to restrict here my discussion to only to unsigned integers. So what we have to do is that we have to end. Okay, so when you would like to multiply, how do you multiply 2 bits? How do you multiply 2 bits? Well, 0 multiplied by 0 equal to 0. If you just take 1 bit of A and 1 bit of B, and I would like to multiply A0 by B0, I just would like to multiply 1 bit by another bit, okay? So 0 multiplied by 0 equal to 0. 0 multiplied by 1 is equal to 0. 1 multiplied by 0 equal to 0. And 1 multiplied by 1 is equal to 1. So only when both bits are 1 and 1, the product will be equal to 1. Okay? So basically, to multiply 2 bits, you end them. It is just an AND operation, logically. Okay? It's very simple. All what we have to do is to AND. But what I have to do, okay, is to AND each bit of A with each bit of B. Okay? Now you have 4 bits in A and 4 bits in B, so this will give me 16, okay, partial bits here, partial, okay, so we have 16, which is 4 multiplied by 4. But in general, I need n squared. Okay, so if you have n bits by n bits, you need n squared n gates to get the n squared product bits. So each one of these bits is a product bit. I have 16 in this example. And in general, you can have n squared n squared and gates. Now, notice that I'm showing them as A0, B0, A1, B0, A2, B0, A3, B0. This is my first partial product. When you take bit 0 and multiply it by all the bits of A, you take bit 1, B1, sorry, and you multiply it by all the bits of A, and so on. Notice the shifting. Okay, so this must be 0 here. This must be 0. This must be 0. Okay, so we have to shift the bits. 0, 0, and 0. Okay, so all of these are zeros. Now notice that if you look here at column 0, it's A0, B0. If you look at column 1, it's A1, B0. It is also A0, B1. If you look at the position of these bits, you look at the indices here. Yani, for example, when you add 1, okay, which is actually bit 1 of A, bit 0 of B. So this is 1 plus 0, it's 1. This is 0 plus 1 is equal to 1. Here we have 2 plus 0 is equal to 2. 1 plus 1 is equal to 2. 0 plus 2 is equal to 2. So basically, by adding, okay, the indices here, I plus J, you get exactly the position of these product bits inside the product. Okay? You get this? So if you look, for example, at this column,
can you repeat it?
For example, you have 3, you have 1. If you add 3 plus 1, you get 4. If you add 2 plus 2, you get 4. And if you add 1 plus 3, you get 4. So therefore, these must be vertically aligned, these product bits. Okay? Notice that 3 plus 0 is equal to 3, 2 plus 1 is equal to 3, 1 plus 2 is equal to 3, and 0 plus 3 is equal to 3. So therefore, these must be vertically aligned. So you know actually how to align these bits vertically. Okay? So this is very important to indicate the position of a product bit. Now, once we have done this, we have n squared product bits in these partial products. What I have to do is that I have to add them vertically, and I have to propagate the carries to produce the final product. So again, I'm showing it here. Okay, I would like to add now the partial products. So this is my first number is A. I'm showing it in capital, A3 down to A0. This is my multiplier here, my 4-bit multiplier. It's B, okay, which is B3 down to B0. And these are my partial products. Okay, these are the product bits. So we have here, okay, 4 partial products. So we are taking each bit of B of my multiplier and multiplying it by the multiplicand. And the operation is very simple. It is just an AND operation. Because remember that when you multiply, you are ending the bits, as I mentioned in the previous slide. So only when you multiply 1 by 1, you get 1. That's basically an AND operation, because when you multiply by 0, you get 0. So this is just simply ending. So this is A0 and B0. This is A1 and B0, and so on. Okay. Now, what you need at the end is that you need this 8-bit product. Okay, so when you multiply 4 bits by 4 bits, you get an 8-bit product. So the product bits are P0 to P7. P0 is the least significant bit of the product, and P7 is the most significant bit of the product. Now, notice that P0 is nothing but A0, B0, so I can just drop this bit. But to get P1, you have to add these 2 product bits vertically, and you might actually get a carry, and the carry has to be propagated, and so on. So how do we add these partial products? We have different possible implementations. I'm going to show you more than one way to add these. I can actually add them horizontally. I need multiple adders. Okay. So when you have many partial products, you need multiple adders. Yes, you need multiple adders. So I can actually add the first 2 partial products. I can add the second 2 partial products. Okay, so let us show a circuit that does this. This is shown in this slide. This will be a 4-bit by 4-bit binary multiplier. So I'm taking here, I'm showing here, you can see I have 16 AND gates, 16 AND gates to get the product bits. So this is B0 ended with A. A here is A3 down to A0. Notice that I'm using 4 AND gates. Here B1 is ended with A. Remember that A is what, as shown, is my multiplicand, is the first number. B is my multiplier. So I'm taking each bit of the multiplier, okay, B0, B1, B2, B3, okay, and I'm multiplying it with the multiplicand, which is A. Okay, so now what we need to do is that we need to add, okay, so this is why I'm using 4-bit adders. Now notice that A0, B0 is the product bit B0. As shown from the previous slide, you just have to drop A0, B0. Okay, so this is my product bit, which is the least significant bit of the product. Okay, so what we need to do is that we can actually add these 2 numbers horizontally, even though there is no number here. We can just put a 0, no problem. Here I can just put a 0, no problem. Okay, so we can just use a 4-bit adder. Notice the 0 here. Notice the 0. Okay, just use 4-bit adders. Now, because we are actually getting a carry, okay, so the least significant bit of this 4-bit adder will be P1. But the other bits, we still have to add them. And for example, in this slide, once we get the sum of these 2 bits, I still have this A0, B2. I still have to add. Once I take the sum of these 2 numbers, I still have to add. Here, I still actually have to add. So you see that this circuit becomes something like this, okay? So you get these partial sums, and then you add them to get the final product. So here we get P2 through P5, which is produced by this 4-bit adder. Notice how we propagate the carries. I still need a half adder and an OR gate to produce the most significant 2 bits, okay? of the product. So this is my 4-bit by my 4-bit, 4x4 binary multiplier that will produce an 8-bit product. Okay. Now this is one way to implement the circuit. So 16 AND gates, and I used 3 4-bit adders to calculate the final product, plus a half adder here because I have a carry that I need to propagate, and this is the most significant bit. And then also I have this carry. Here just an OR gate will be sufficient. Okay, without going into the math. Well, the math is just based on the previous slide, this slide. Okay, so we are adding here the first 2 partial products. I'm also adding these 2 partial products. I'm taking their sum and then adding them. Okay. And then at the end, when I get actually the carries, I use them to produce the most significant 2 bits of the 8-bit product. So you can implement a 4x4 bit binary multiplier this way to get an 8-bit product. Things become much more complex. Of course, if you are multiplying 8-bit by 8-bit, you will need actually more adders. You will have a tree of adders. In this example, I only needed actually 3 4-bit adders. So the number of 4-bit adders is only 3 in this example. Of course, in addition to the large number of AND gates, plus like a small half adder and an OR gate to produce the most significant bits of the product. Now you can do it differently. We can use carry save adders. Now the problem with this implementation is that as this becomes larger and larger, as a multiplier, you need more adders. Now these adders become large. There are propagation delays. If you are using a ripple carry adder, there will be propagation delays, and this is going to increase the delay, in the circuit to produce, the final product. So the idea is to use something which is carry save adders. So carry save adders are used to produce efficient multipliers in the hardware. Now the difference between a carry propagate adder and a carry save adder is that the additions of the bits are done in parallel. Now notice that in both cases we are using, if we would like to add 2 numbers, I can use a carry propagate adder. So in the case of a carry propagate adder, we propagate the carry. This is the carry propagate adder that we already know from the 202 course. It's a very simple adder. Now notice that here we are adding 3 bits, A0 plus B0 plus some carry in. Now this is going to produce a carry out. This carry out, for example, this can be C1. Let me just write C1 here. This carry in can be C0, right? So let me just write C0. Terrible handwriting. I'm just writing with a mouse, sorry. And so on. So basically, you can actually propagate these carries. So we are adding 3 bits. So each one of these is just, so this plus here, which is shown inside this box, is a full adder. It only adds 3 bits. It produces a sum bit and a carry out, and this carry is propagated to the next full adder and so on. So this is what we call a carry propagate adder. So here I'm adding, let us say, 32 bits plus 32 bits. So this will be a 32-bit adder. So notice that the bits are numbered from A31 down to A0, and the carries are propagated. So because of this, this is going to increase the delay. Now, another way of doing this is what we call a carry save adder. So rather than producing here the carries, propagating the carries, I can save the carries. So I'm calling it here a sum and a carry, but I'm using prime here to indicate that these bits are different from these because I'm not propagating the carry. And because I'm not propagating the carry, I'm saving the carry. All of these bits can be added in parallel. So I'm using the same 32 full adders, but the bits are being added in parallel, and therefore this will reduce the delay and make the addition a lot faster. But I still have to add the carries, but I will do that later. So these carry save adders are used in multipliers. They are used in multipliers because you are adding multiple numbers, and therefore this will make the addition of the partial product a lot faster in the case of carry save adders. So let us do it. Let us do it actually for 4-bit by 4-bit. Now I'm going to do the addition vertically, the same way that I did it actually in my example by the paper and pencil. So I'm going to add the bits vertically. So I'm going to add these 2 bits vertically, these 3 bits vertically, and so on. Now I can add 2 bits using a half adder. I just need a half adder to add 2 bits vertically. But I need a full adder to add 3 bits vertically. But when I get a carry, I have to propagate the carry. So I can actually use here carry save adders to add all of these bits in parallel without propagating. So I can use it like this. I can produce here a tree, okay, of adders, okay, full adders or half adders. If I'm just adding 2 bits, I'm going to use half adder as indicated in this box. So HA here is a half adder. If I'm adding 3 bits, I'm going to use a full adder. So notice that most of these are full adders except, okay, when I'm adding only 2 bits. Now, when I get notice that all of these additions are done in parallel. So you can see that the first row on top is a carry save adder. The next one is also a carry save adder. Only for the last row is a carry propagate adder. So by building your multiplier this way, you can reduce the delays and you can make the production of the final product a lot. You can actually reduce the delays and therefore the multiplier becomes faster, okay, in the hardware. So we are just adding the bits the same way they appear, okay, here, okay, in this slide. Notice that here I'm adding A1 B0 plus A0 B1. Of course, these are produced by AND gates. I'm not showing the AND gates here. I'm just showing A0 B1, A1 B0. So I'm just adding them with a half adder to produce P1. Notice that for P0, I don't even need an adder. It is just A0 and B0. That's actually for P0. Okay, this is very simple. But when you would like to add these 3 bits, as shown in this slide, A2 B0, A1 B1, A0 B2, I can add them vertically, okay, without propagating the carry. I can just use here a full adder to add these 3 bits, this plus this plus this. Notice that I'm producing a sum and a carry. The carry is propagated to the next full adder, and so on, okay? So basically, I'm adding these partial products, okay, vertically, these bits, these product bits. I'm adding them vertically using full adders. And then when I get a carry, I propagate the carry, okay, and so on, using actually more full adders. Sometimes I use a half adder when I would like to add only 2 bits. Sometimes I use a full adder. In fact, most of the time I use a full adder, but sometimes I need to use a half adder, okay, when I'm adding only 2 bits. And this way I can produce all my product bits this way, okay? So when you add the bits in parallel, we call it a carry save adder. So here I have carry save adders, except in the last row, I need to propagate, okay, the bits, and this is called a carry propagate. Okay? Any question about this? So this is the hardware that does the multiplication. Of course, it gets larger and larger, okay, when we are multiplying large numbers. Okay, so in this example, it was only 4 by 4 bit multiplier, okay, and the product was only 8 bits. But things become much larger and cannot really fit on one slide when we are dealing with a large number of bits. Questions? Everything is clear?
Yes, doctor.
Okay, so this is really how the designers design multipliers in the hardware. So now this is a summary of a fast multiplier. Okay, so if you would like to multiply n bit by n bits, you need n squared the number of AND gates. N squared, okay, AND gates. And these will produce n squared product bits in parallel. The most important thing is that it's going to produce them in parallel, okay? We need many adders to perform the addition in parallel. People use carry save adders to reduce delays. This is really the idea of carry save. And the cost is big O of n squared, where n is the number of bits. So if you would like to look at the complexity of this fast multiplier, is big O of n squared. Okay. So where n is the number of bits in the multiplicand and the multiplier. Okay, so the size, the area of the multiplier on the chip is going to grow quadratic, okay, with the number of bits, n squared. Next, I need to talk about division, integer division. So we have seen multiplication, and in the case of multiplication, people can build really very fast multipliers today in the hardware, although the area is large, but they can be very fast. Now, in the case of division, let me talk about unsigned division, because we have signed and we have unsigned, depending, of course, on my integers. So let me start first with unsigned division. Suppose I would like to divide this 8-bit number here, which is 217, by this divisor. So this is called the dividend. The first number is called the dividend, and this is called the divisor. So the divisor here is what? It's 11, right? It's 11, right? So this number in binary is equal to 11 in decimal. Right, so let us do this division. So what I would like to do first is that I'm going to attempt to divide 1 by the divisor, but this will give me 0. Okay, again, my pen tool. Let me use here. Okay, I have a pen tool here. So I'm going to try to divide this one here. Okay, so this one by 1011. Of course, this one is less than the divisor, so I'm going to put a 0 on top. Then you try to divide 11 by the same divisor, you get another 0. Then you try to divide 110, which is 6 in decimal. 6 is less than 11, you put a 0. Then you try to see that, okay, now if I would like to divide, now you can see it's actually very crowded. Okay, so let me just erase all my ink. Okay, so now what we did is that we got 0, 0, 0, right? Now I'm going to try to divide 1101. Now 1101 is 13, and 13 is larger than 11. Okay, so because it is larger, then we just put a 1, okay, on top. And then we subtract, because 1 multiplied by the divisor is 1011, and we subtract. Now, when you subtract, you will get 2. This is actually 13 minus 11. You get 2. Okay, of course, you can say 1 minus 1 equal to 0. Then 0 minus 1, you have to borrow. So it becomes like 2 minus 1 is equal to 1. And we have to borrow this one. So this becomes 0 minus 0 is equal to 0. And 1 minus 1 equal to 0. So therefore, the difference is equal to 2. Okay. Now we continue. We drop this one. So it becomes 101. It becomes 5. 5 is less than 11. So therefore, we put 0. Now, this 0 is very important. Now, the zeros here, the 3 zeros that appear to the left, are not important because really these zeros are not significant. But this 0 is significant. So therefore, okay, we put a 0. We drop another 0. So it becomes 10. 10 is still less than 11, right? So we put another 0. We drop the next bit. So this number is what? This is 16 plus 4. It's 20. So 20 is larger than 11. So we put a 1. So when you put a 1, you have to subtract. So we say minus the divisor. So when you subtract, this is subtracting 20 minus 11. So it's just 9. Okay, of course, you can do the subtraction. The hardware will do it in binary, definitely. But I'm just showing the final result. And then you drop another 1. Now, this number is what? Now, this number is 19. It's 16 plus 3. And it is larger than 11. So we put a 1. And we subtract. Now, when we subtract, we get 8. This is 19 minus 11 is 8. So this is my final remainder. The remainder is 8. Now, if you look at the quotient that appears on top, this is 16 plus 3, which is equal to 19. So I got a quotient which is equal to 19, and I got a remainder which is equal to 8. Now, this is the same thing as doing the division by using a calculator in decimal. If you divide 217 by 11, you will get the quotient equal to 19, and you get the remainder is equal to 8. In other words, if you multiply the 19, the quotient, by the divisor, which is 11, and add to it the remainder, you get the 217. You can always verify this. 217 is equal to 19, which is the quotient, multiplied by the 11, which is the divisor, plus 8, which is the remainder. The remainder must always be less than the divisor. It cannot be equal, and it cannot be greater than the divisor. If you have done the division correctly, the remainder must be strictly less than the divisor. It has to be between 0 and the divisor. Okay? This is unsigned division, which is done by paper and pencil. Any question? Okay? It's very simple. What you have to do is that you have to shift and subtract. That's it. So we check how big a number can be subtracted, creating a bit of the quotient on each attempt. Okay, so the bit here can be 0 if the number actually cannot be divided. If it's less than the divisor, you put 0. If it is larger than the divisor, you put 1, and you can simply subtract. You can design a sequential circuit that does this bit by bit. Yeah, and you can take each bit of the dividend and you can repeat like this. Notice that my quotient is 8 bits. I'm only showing here 5 bits because the most significant 3 bits are 0, 0, 0. Okay. So this is unsigned division. It's done using shifting and by subtraction. That's it. Very simple. That's how we do binary division. We can design the hardware, a circuit that does the division. But we got two things. We got two things in the case of division. Not only the quotient. Okay, this is integer division, by the way. It's integer division. So we don't really get a real number. We don't really get a fraction. We got a remainder. Okay. So notice that we got two things. We got the quotient, which is shown on top here. This is 19. Okay. And we got this number here in binary, which is 8, which is the remainder. So we got two results. Okay. In the case of integer division, we got two results, not just one, two. Okay. Fine. So how about signed integer division? Okay, we can of course design circuits that will do also sign, like we did in the case of signed multiplication. But for simplicity here, I'm going just to remember the signs. Okay, the signs of the dividend and the divisor. Okay, so remember them and convert them to positive. Yani if the number is negative, take its 2's complement. Obtain the 2's complement if the number is negative. So you are converting it. When you take the 2's complement of a negative number, you get the positive value. Okay, and then do the unsigned division that we have done in the previous slides. So only divide the positive numbers. Do not divide it if it is negative. Take the 2's complement and then divide the positive numbers. So do the unsigned division and compute the signs of the quotient and remainder. So we calculate the signs. In the case of the quotient sign is the dividend sign XOR the divisor sign. So you look at the signs of the dividend and the divisor. If the signs are identical, you get positive quotient. If the signs are different, you get a negative quotient. Yani, for example, if both are positive or both are negative, you get a positive quotient. Yani, negative divided by negative is positive. If you have one of them is positive and the other one is negative, you get the quotient to be negative. The same thing in the case of multiplication, by the way. If the signs, we use the XOR. XOR, the nice thing about the XOR gate is that the XOR will give you 1, okay, if the inputs are different. Yani 0 XOR 1 or 1 XOR 0 will give you 1. If both of them are 0 or both of them are 1, you get 0. Okay, that's exactly what we need for the sign of the quotient. In the case of the remainder sign is equal to the dividend sign. So the remainder and sign is equal to the sign of the dividend. Okay. I'm going to show you some examples. Now, if it turns out that the result is negative, we did the unsigned division. We produced the positive result. But if it turns out to be negative, we take the 2's complement. So we take the 2's complement of the positive result or the unsigned result to convert it to negative. Right. So let's take a look here at signed integer division. I have some examples about that. So if I would like to divide plus 17 divided by plus 3, notice that the two numbers are positive. So the quotient is positive and the remainder is positive. Okay, so this is case number 1. So we have 4 cases because the dividend can be positive or negative. We also have the divisor can be positive or negative. So there are 4 cases in total. So positive divided by positive will give you a positive quotient and a positive remainder. Now we got 5 here because this is integer division. If you multiply 5 by 3, which is my divisor, you get 15. Add to it the remainder, which is 2, you get the 17. So notice that the dividend is equal to the quotient multiplied by the divisor plus the remainder. Okay, we don't even get 5 point something because this is integer division. So we stop at 5. And we say that the remainder is equal to 2. Okay. Now, suppose that I would like to divide a positive by a negative. The quotient must be negative. If one of them is positive and the other one is negative, or vice versa, let us say negative 17 divided by plus 3, you get negative quotient. So if one of them is positive and the other one is negative, it does not really matter. You get a negative quotient. But how about the sign of the remainder? Now, the sign of the remainder is the same thing as the sign of the dividend. So here I have plus, I got plus 2 as a remainder. Here I had negative 17. Here I will have negative 2 as a remainder. Now, why? Because you see that if I multiply negative 3 multiplied by negative 5, this will give you plus 15. Plus 2 will give me the plus 17. Here, if I multiply 3 multiplied by negative 5, this will give me negative 15. Minus 2 will give me negative 7. So for this reason, the remainder, okay, in the third case, when I have dividend, turns out to be negative. Whereas when I have a positive dividend, the remainder turns out to be positive. And the last example, when I have both of them to be negative. So negative divided by negative will give me a positive quotient. But the sign of the remainder is the sign of the dividend. Here, the dividend is negative, so therefore the remainder is also negative. So if I multiply negative 3 multiplied by 5, we get negative 15. Minus 2 will give you negative 17. Okay? So this equation must always hold. Dividend is equal to quotient multiplied by the divisor plus the remainder. Okay? Remember this in the case of integer division. Okay?